Okay, so before we start with the new material, I would like to go over the homework problem with you. So last time we talked about one of the important homework problem. That's this one, and we indicate that I have already indicated the main steps in the proof. So I analyze this to you. So here I just want to show you the actual proof, so you can, but you need to practice by yourself. Okay. So in this case, you can see from the analysis that we need xn minus x to be less than square root x times epsilon. Square root x is a fixed number in this case, obviously. So then we're going to have that. You can see the final inequality. Well, you turn the final inequality as the absolute value xn minus x divided by these two things. Then you can see you can just throw away the xn term. So that means this is less than that. And then you can see xn minus x is less than square root x divided by epsilon. So that square root x cancel. So this gives you just the epsilon. Okay. So this is this is what happens. So therefore that's so this is an easy one. So I will also show you the other one. The other one is that we have two sequences Sn, Yn, and assuming that the limit are not equal. So you are supposed to show that when n large enough, the xn is not equal to yn. And also I analyzed the situation with you last time. Now presenting the detailed proof. So checking whether this is coincide with what you have come up with or not. Some steps is kind of new, so I'm going to do this in detail. So that's the detailed proof. Okay, basically you see that you're assuming the x, y to be the limit, they're not equal. So therefore you take the half of the distance as your epsilon. So when n large enough, you can see that the both xn minus x and the yn minus y will be less than this epsilon. So this epsilon equal to half of the distance. And now the key is that when n larger than k, okay, you are going to have the following inequality, which will give you the result. So you begin with xn minus yn, okay? Now this time you insert 4 terms into the expression. Basically you insert minus x plus x, minus y and y. So you can see that the x cancel, y also cancel, okay? So the reason doing this is because I want to make x minus y appear, because this is something I know. Okay, all right. So I underline this by the red of these 3 terms. Okay, so the first thing xn minus x, that's middle one x minus y, then is minus, or you can say minus yn minus y. Okay. So you have to play around the triangle inequality with these 3 terms. What you do is here, eventually you will get from this estimate the absolute value x minus y minus the sum of both individual difference. Now, how can we get that? We have to apply the triangle inequality twice. So this is what we're going to do. So I'm going to rewrite this 6 term in a different order. So we begin with x minus y. Then you can plus xn minus x. Then, or you can say minus yn minus y or y minus yn. It doesn't matter. Okay. So what do you do is first, we're applying the second kind of triangle inequality on as 2 terms. You think about this 6 terms, 2 terms. One is x minus y, that's 1 term. The other one is xn minus x minus yn minus y. Using the second kind of triangle inequality, you'll get this. And this is something we learned previously, right? And then you concentrate the second term on the right. So there are 2 portions there. The one portion xn minus x. The other is yn minus y, right? And then you apply the regular triangle inequality. Now, when you apply regular inequality, things getting bigger. But however, you know that there's a subtraction sign in front of it. So if you use the regular inequality on the second term, the whole thing will get smaller. So you can continue with this inequality sign in this direction. So that's how we get that. Okay. And then you can see you keep x minus y term. then you can see that the other two after the minus sign, then these two terms are less than epsilon, right? So replace this by epsilon, and we know epsilon equals 1/2 of the distance. So you will get the following. You get x minus y absolute value minus absolute value x minus y. Okay, so this gives you 0. Now, why this gives us result? Because this means that in all the connection in the middle, you have a strict greater than sign, greater than. So this implies that absolute value of xn minus yn is strictly greater than 0. So this shows that xn not equal to yn. So that's the solution. Okay, so you can study it by yourself. So this is how we handle the number 7. Okay, so today we're going to continue. So last time we talked about the converging, the monotone convergence theorem, and we showed the one direction. Now today we're going to finish the other direction. Then we can see some examples. Okay. Now today's example is extremely important. So showing the other direction, it means that we're assuming that the xn, the monotone sequence has an upper bound. It's bounded above. And then we're going to show that this sequence carries a limit. Okay, the limit is actually the least upper bound. So this is what we're trying to do. Okay, so we're going to do this at time. So we're going to show that limit xn equal to x. Okay, so what we're going to do is for any epsilon, or for any epsilon. Now, since we know that x is the supremum, it's already the least upper bound. Okay, so therefore the x minus epsilon is not going to be upper bound anymore. So therefore, by the theorem 1.5, you can see that there is some term. Okay, the term is obviously less than x. Okay, because x is the least upper bound, but that term should be greater than x minus epsilon. Okay, obviously you can find such a term. Then you can see since xn is increasing, so this shows that for any other term where n is greater than n naught, we're going to have that the xn is greater than xn naught, which is greater than x minus epsilon, right? But on the right side, the xn is less than x, and x is less than x plus epsilon. So you can see this is a complicated inequality. There's 4 inequalities involved here, but we are only concentrate on the left, middle, and the right side. So if we throw away the unimportant terms, so this will imply that x minus epsilon is less than xn, okay, and less than x plus epsilon. Because throw away the middle term here, so you'll get this. So then I move the x to the center. So that means I subtract the x on all these sides. So you will get the minus epsilon less than xn minus x and less than epsilon. So this is what we want. And this is just the inequality with absolute value sign. So this shows that xn minus x is actually less than epsilon. So this shows that xn goes to x. So that's the proof. Okay, so the proof of this result is kind of long, and there's a lot of technique involved, and so you may want to study the proof again by yourself in the other class. Now here, it's more importantly, we are going to see some example how to use this result to solve the practical problems. Okay, so there are very special type of problem involved here. So that's what we're trying to show. Now here we are going to have a sequence xn, and the sequence is defined by formula, recursive way, okay? So this means that this sequence is defined this way. I know x1 is considered to be 1. Then the next term is determined by the previous term by the formula that xn plus 1 equals to 2n plus 3 divided by 4. Okay, so this is the how we define the formula, because you define x1 from 1, you can define x2, then you can define x3 using x2, right? So in using this recursive relationship, you can define all the tangent sequence. So in this sense, the whole sequence is defined by this formula. So this is a very special way to define sequence. And for this kind of sequence, our convergence theorem criterion can apply here and to get the limit to prove the convergence. Okay, for this problem, what we want to do is we're going to show that this xn is increasing and bounded with limit xn equal to 0/2. So this is our goal, okay? Now, why we need to prove increasing and bounded? This is because that once I can show this is increasing and bounded, okay, then you can see that by the criterion of convergence, the sequence has a limit. Now, once we confirm that the sequence carries a limit, then from this formula, I can take a limit on both sides. So you have a limit, later you are going to see that there's the limit should satisfy certain equations. Then by solving this equation, you can get a limit. Okay, so that's why this case is very special. And now, so the key is to show that the sequence is increasing and bounded, and which will guarantee the existence of limit. Now, how do you see this sequence is increasing and bounded? And here, the special way to do this is to use the induction, the method of induction. And we learned the method of induction from the 415. Okay, so we use induction to prove that. Okay, and xn is increasing and bounded. Okay, so how we can do that? So let's use induction. It's checking the first time first. So when n equal 1, now we're going to show that the whole sequence is bounded by 2. Now, why we can find that that upper bound is 2? That's another question. And just by experience, by practicing, you can guess such a bound. Okay. So we're going to use induction to prove both. To prove it is bounded and increasing, we're going to use induction at the same time. Normally, it's a 2 procedure, right? But we combine these 2 procedures together. So for n equal 1, first I show that I will say x1 is less than 2, okay? And then we're going to show that x1 is less than x2. And this is easy because x2 is determined by x1. So actually x2 is equal to 2 plus 3 divided by 4 and 5/4. So obviously this is greater than 1. So you can see that we verify that x1 is less than x2, okay? So that's the first step in the induction. And now let's make assumption, what we call the inductive assumption. And let's assume that xn is less than 2, as also xn is less than xn plus 1, okay? And then we'll go to the next step, the higher level, to see whether it is still true. If it is still true, then the induction works, will prove the result. Okay, so let's look at xn plus 1. I know that xn plus 1 equal to 2xn plus 3 divided by 4. Okay, so this is equals to 4 plus 3 divided by 4, and which is equal to 7/4, which obviously is still less than 2. So if xn less than 2, then xn plus 1 is still less than 2. So that's good. But then I want to apply to the increasing side. So I want to look at the whether it is still true about this term is increasing. Now this can be handled this way. Now since xn is less than xn plus 1, so therefore we're going to see that if you times 2, the relation still hold, and plus 3 divided by 4. So the relation still hold. And these two relations actually give you the xn plus 1 and also xn plus 2. So naturally you can see that from xn less than xn plus 1 will imply that xn plus 1 will less than xn plus 2. So therefore by induction you can see that xn is increasing and bounded at the same time. Okay, so that's how we apply the induction to prove its increasing and its boundedness. And so both will imply that the sequence is actually bounded. Okay, the sequence is bounded. And hold on just a second. Yeah. So what our goal is to choose a limit equal to 3/2. Okay. Now, since the sequence is bounded and increasing, so by the theorem 2.8, the limit xn exists. Therefore, I can say that the limit equal to x. And now we are going to take the limit on both sides of these equations. And then using 2.7, because using combination theorem, you can get this limit should satisfy the same relation. That's x equal to 2x plus 3 divided by 4, which will give that exactly that x is equal to 3.5. Okay, you can verify, you can check this detail. Okay, I can see there's a question. Okay, the question, how do we know that the limit was 3/2 in the beginning? Because this is an exercise problem. So if you are giving you a real sequence like this, you don't know. No one knows. So you can guess, okay, or predict, okay? But this is an exercise problem. So we know the limit equal to 3/2. Now this is a very good question, okay? For this kind of problems, there's no general way you can predict what is the limit. Or you can see, okay, you can the other way. Now, there's one way to think about this way. Now, you have to assume that the limit exists. Now, if the limit exists, then the limit should satisfy the same relation, okay? Should satisfy the same relation. And so therefore, by solving this equation, like x equal to 2x plus 3, you will get the x equals 3/2. That's the only way you can predict the limit. But the question, this is based on the assumption that the sequence is increasing and bounded. Okay, without proving it is increasing bounded, you cannot confirm that the limit always exists. But here is that if the limit exists, then the limit has to be 3/2. And this can be seen from the relationship. Okay, now the real question is boundedness, because we also need to show that the sequence is bounded. And boundedness is not observed from the relation. So this must be, you can guess it or try it with a different number with induction. Okay. Another thing is for this kind of problem, now in this case, the sequence is increasing in bounded, right? But it may happen that the sequence is decreasing in the bounded. Then still you can have the same result. But if the sequence is no longer increasing or decrease, is behave the other way, then you cannot use this argument to get the limit. Okay. All right. So let's look at this another question. Okay. Now there's another question is x equal 1. Then xn is denoted by square root 2xn. So this is another example, and in which you want to choose a limit xn equal 2. Now, okay. Now first suppose the limit exists. So if the limit exists, so suppose the limit equal to x. So this means that x should satisfy the same relation. So x should equal to square root 2x. You solve this equation, you'll get x equal to 2. No doubt. Okay. But the question is, how do you prove it is bounded? Or you can prove this is a monotone sequence and it is bounded. So we use the induction to show that xn is increasing and bounded, okay? So what we guess is the bound is still 2, and also it's increasing. Now when n equals 1, this is obvious. x1 equals to 1, obviously less than 2, okay? And also x2 equal to square root 2 is greater than 1. So you can easily have x1 is less than x2. There's no problem with this, okay? Assuming that xn less than 2 and xn less than n plus 1. So you're going to get, first, you should look at the bounded side. So xn plus 1 equals square root 2xn, which is less than square root 4. Because why? Because xn less than 2. Okay, so therefore the xn plus 1 is still less than 2. Okay, so the boundedness, you can see induction works. And also, increasing side is also worse, because once you have xn less than xn plus 1, if you times 2 as square root, it still carry the same relations. So this indicates that xn plus 1 is less than xn plus 2. Okay. So by induction, this is increasing and bounded. Okay, so this is even simpler than previous example. And then you can see that you can confirm that the limit exists and call the limit to be x. And then you can see that the x satisfies the relation. So x equals to square root 2x. So that's how you get x equal to. Okay. So that's a second example. Now today, I want you to, so this is the things what I'm going to cover today, okay? And so one of the additional homework I want you to work with is this kind. So x1 equals to 1/2. The xn plus 1 is more complicated, equal to xn3, a cube plus 2 divided by 3. Okay, so this time I didn't give you any limit. Okay, I didn't say what the convergence is. So we want to show this sequence converging. Okay, you can see the sequence bounded or converging or whatever. Okay, so once you confirm the sequence carries a limit, then you can see limits should satisfy the same equation, right? So this equation is a little bit more complicated. It's a cubic equation. I mean, there's a power 3 involved. So you have to be careful to solving this equation. I will provide solution next time, but you need to work on this, number 8. Okay. So far we have covered the 3D, okay, and 2D, 2C. 2C is the previous. Now we have 2 more sections to go for this chapter. So there's the rest of this section are very theoretical, but very important. So I want to go slowly and carefully. So the one of the things that's 2.9 is theorem 2.9. It's called Bolzano-Weierstrass theorem. So this is a very deep theorem, and it is very important for the later lecture. So I want to let you take a look at this theorem first before next time we're going to prove this theorem. So the statement of this theorem is very simple. Now, in all the previous lecture, we're talking about converging sequence. So every time you have a sequence converging, we are thinking about the sequence converging. We're thinking about what the limit is. How do we prove the limit? Now, for this theorem, we're not dealing with converging sequence. We just consider a general bounded sequence. So for this general bounded sequence, we want to show that the sequence has a convergent subsequence. Okay, that's the result. Okay, so we're going to continue the lecture next Tuesday. So today, I just want to stop here so you will have more time to work on your homework problem. All right? Any questions? Okay, no questions, then we can stop here today. Today's lecture is short, all right? Okay, thank you.
Thank you.
Okay.